Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. Today we'll be focusing on smart meter data analytics. So please try to understand a smart meter itself is a device which has its inherent capacity to process some of the data, and that process, that type of the capacity to handle the data and processing it is known as smart meter data analytics. Now, first of all, let us understand what is a smart meter, because it's an energy meter, we all know that, but why we call it is a smart. A smart meter is a part of a advanced metering infrastructure, so-called AMI, which also includes communication network and data management system. It enables automatic two-way communication between the utility and the consumers. Unlike traditional meters, smart meter provides real-time or near real-time data on electricity consumption, high resolution usage records capturing consumer behavior and usage patterns, remote access and control for billing, connection, disconnection, and fault detection, load profiling, which records detailed electricity usage over a time, consumer behavior analysis enables personalized services and segmentation, demand response support helps utilities shift or reduce load during peak hours, anomaly and theft detection identifies unusual pattern or unauthorized use. Billing automation provides accurate and timely billing based on accurate or actual usage. Now, the global deployment and role of smart meter, if you see, smart meters have seen wide adoption globally. Perhaps in US there are 70 million, and in UK there are 2.9 million, and India will be happy to know we have 29 million smart meters deployed. Now, what are the research initiatives in smart meter data analytics, which is a very, very important part. As I told you, once you get those huge data, so-called big data, we'll be processing in the server or cloud level. However, the smart meter itself, can carry out bit of analytics. So let's understand. In United States, National Science Foundation (NSF) fund cross-disciplinary research in smart grid big data analytics. That means they do encourage such kind of research to be performed. In Denmark, Center for IT Intelligent Energy System in cities called Innovation Center support machine learning based smart meter analytics. In Europe, European Statistical System Network, ESSNet, big data project involves Austria, Denmark, Estonia, Sweden, Italy, and Portugal, focusing on data access and methodology deployments. Now, even in China, National Natural Science Foundation of China (NSFC) and National Key R&D Program fund big data analytic projects, including it includes almost 863 programs. Switzerland and Germany, BITS to Energy Lab, ETH Zurich, University of Bamberg, University of St. Gallen focus on customer segmentation and efficiency services. Cybel Energy Institute funds global collaborative research in energy data analytics. Now, even in India, India's smart meter research focuses on data analytics for load forecasting, anomaly detection, and consumer behavior modeling. National programs like NSGM, National Smart Grid Mission, and Smart Meter National Program drives R&D and large-scale AMI deployment. Utilities and academic institutions collaborate to develop AI/ML-based tools for smart, efficient grid operations too. Now, SS 2017 survey of 136 utilities from 24 countries highlights the use of analytics in energy forecasting, smart meter analytics, asset management, grid operation, customer segmentation, energy trading, credit collection, call center, and demand response programs. However, this is not limited to this dozens of actually applications, whereas startups are emerging to offer analytics driven insights and services using smart meter data. There's many startups are working on this area, and collaboration between academia and industry is also increasing to address the energy data analytics talent gap. Now, when you talk about actually open load data sets, now there are different data sets currently available. Some of them are in public domain and some of them are not available to public, but they are available for research. Uh, Customer behavior trials launched by the Commission for Energy Regulation, Ireland, to study energy usage behavior across demographics using smart metering. This is perhaps being executed in Ireland, and it is related to household data and behavior trial, demographics, lifestyles, and home sizes are being considered. Now, low carbon London, that is another data set, trial involving over 5,000 households to study the impact of low carbon technologies on electricity networks, being executed in London, UK, and it's basically household data and smart meter data, time of use tariff surveys are being considered. And then we have actually Pecan Street, which talks about actually minute level electricity consumption data from 500 homes in Austin, Texas. So Austin, Texas, USA, which is again, the household data, and whole home and appliances level data are being used. Building data genome, which is a 507 building meters, mostly from university campuses, uh, and various mainly universities data has been taken, and they are for buildings, and whole building electricity meters are being used for data collection. Then we have another data set name called UMass Smart, collected by Mass Smart Microgrid project, includes minute level data of 400 homes, and it's being executed in USA for household data, and 1 minute granularity for 1 day are being captured. Then one more data set called Us Grid Resident, data from 300 residential consumers with rooftop PV over 3 years, carried out in Australia per household, and smart meter rooftop PV generation data are being used. And then Osgrid substation, another case study where load profile of 180 substations from 2005 onwards are being captured and recorded. Now, then we have actually GFCOM 2012, and then you have GFCOM 2014. They are basically hourly load and temperature data from January 2004 to July 2008 from 11 weather stations, okay, being captured. And GFCOM 2014, which is hourly load and weather data from 25 weather stations are being captured. Then we have ISO New England data, where publishes system level load and temperature data for 9 Junes monthly and being performed in USA. Moving to data processing at different level of smart meters, as you could see that we have a DSO sitting here, whose responsibility is to look after the network security and economic operation. And there's a retailer which is sitting here, and the electricity information which is coming to consumer, and where we have actually many home energy management system and transitive energy happening, and there is an aggregator who is really responsible for demand response and energy efficient studies. And we do have actually smart meters and thousands of smart meters connected at different buildings and blocks. And it is also expected that, how, the customers can participate in a business model at the demand side. And this activity is possible only with help of a smart meter and its effective data processing. So now when you talk about smart meter data analytics, as you can see that we can do load analysis, we can do load forecasting, load management, and further in load analysis we can do big data detection, non-technical loss detection, and load profiling. And in case of load forecasting, we can do forecasting with individual meters, without individual meters, and probability forecasting is possible. And we can do characterization of customers is possible, demand response activity, its marketing and implementation. And further, we can also have actually connection verification, outage management, data compression, and data privacy. So to do this, actually, we need to have many techniques, which is time series analysis, and then dimension reduction, and outlier detection, classifications, and then clustering, deep learning, low rank matrix, compress sensing, online learning, etc. are going to be my different techniques that can be embedded. So, to conclude, I mean, here for the smart meter data, which is available to me, how we can process and make best use of those data for system efficiency. Now, this is one sort of actually load analysis we are carrying out. So, this is basically typical normalized daily residential load profile. And you could see very interestingly, the load profiles are not completely clustered. So, you can have different varieties of load peaks that happens from one residence to other. But as a whole, if you see, most of the loads are actually being clustered in this zone, but however, there are few spikes that is possible from time to time. So figure 53.4 displays 8 typical normalized daily residential load profiles using the k-means clustering algorithm applied to the IRIS residential load database. And load profiles vary significantly across consumers and days, showing high volatility and uncertainty. So what we wanted to say that when you have actually a group of customers or consumers, the load patterns are not necessarily to be similar, and a majority of the loads are common, but you can also see some spikes or the peaks that they're happening or occurring at different point of time of the day. Now, load profiling helps identify typical consumption pattern of individual consumers or groups. These profiles can support load forecasting, demand response program planning, and many other aspects. Now, one more important part, when you collect the data, how do you detect that what are those data are not useful to me? So, bad data includes missing data or unusual patterns caused by their unplanned event, failures in data collection, communication, or entry. Detection methods are categorized as probabilistic, statistical, and machine learning based approach. Three modeling approaches commonly used. They are time series based methods, low rank matrix technique, and time window based methods. So these are the methods that are being commonly used for bad data detection. Let us focus on the time series based method for bad data detection. There are many time series based methods do exist for detecting bad data. Optimally weighted average method, which combines data from neighboring time points and is used for both real time and historical data correction. Autoregressive with exogenous input combined with artificial neural network models are also used to detect outliers by analyzing residuals, capturing both linear and nonlinear relationship in the data. Generalized, extreme, studentized, deviate test and Dixon's Q test, which is very popular, are used to identify outliers in large and small database respectively. Canonical variate analysis also used for clustering recovered load profiles, and linear discriminant analysis is used to classify abnormal electricity consumption. We can also get into low rank matrix techniques, and these methods utilize spatial and temporal correlation in electricity consumption data to detect and correct anomalies. They're applied for data cleaning and imputation, including alternating direction method of multipliers based distributed matrix techniques that allow privacy preserving communication between multiple consumers. Both offline and online low rank matrix algorithms for anomaly detection and corrections. And there are a couple of limitations, these techniques may not perform well when data remains constant over a period, and additional data preparation is needed to handle such cases. Moving forward to time window based methods, where segmented clustering is one of the time window based method where load profiles segmented in time windows and clustered for recovery of missing data. Sliding window plus classifier is a very important concept which contextual anomaly detection using overlapping windows. Online detection, lambda architecture, real-time scalable detection method also capable of parallel processing for large data volumes. Now, when we talk about energy theft detection, though we talked a little bit, so energy theft modifies a smart meter data intentionally that can persist over time. So how we can use those detection, bad data detection schemes for energy theft detection? How do we know that there is a leakage of current? It is categorized as bad data because that is not expected to be the real. If you have a residential pattern, we have a load pattern, but when it's being theft, suddenly you see there is a zero consumption by the smart meter. So, which is not acceptable to me. It's a bad data. Evening 7 p.m. and the meter is not showing me any current, seems there is something wrong. So it is characterized as bad data, but unlike random errors, it is deliberate and systematic. So detection can be performed using only smart meter data or in combination with power system data, example, node voltages. Methods using smart meter data falls into two main types. One is supervised learning and the second one is actually unsupervised learning. Now, when you go for load profiling, another important concept using smart meter data, load profiling classifies consumers or load curves based on electricity consumption behavior. And two main approaches, as we discussed, is direct clustering, and the second one is indirect clustering. In case of direct clustering, apply directly on smart meter data. However, in case of indirect clustering, involves feature extraction before clustering. So direct clustering methods, which is the basic common techniques, k-means, hierarchical clustering, self-organizing maps, and so on and so forth. Now, there are many issues. The issue number one is my data resolution, where smart meter data with greater than or equal to 30 minutes interval is generally reliable. Whereas in time series nature, the time dependent clustering, example, dynamic k-mean is required. And in case of two-stage clustering, actually stage 1 where we do local clustering, and in case of stage 2, we do centralized clustering on cluster centers. And the main benefit of two-stage clustering is reduced computational complexity and support distributed processing. Now, in case of indirect clustering method, mainly actually it's a dimensionality reduction technique where principal component analysis PCA, which reveals consumers types and patterns over time and space, combined with k-means for effective classification. And we also do deep learning mechanism which compress load profiles followed by locality sensitive hashing, that is LSH, for clustering. Now, load characteristic based features where features generation using conditional filters, shape signatures, profile errors and calibrations, subspace and projected clustering increase robustness to noise. Time based behavior features identified 4 key time periods: overnight, breakfast, daytimes and evenings. Derived 7 attributes from these periods to cluster consumers as well as bootstrap used to verify its robustness. Now, the important tool is about the load forecasting, where normalized hourly profiles of a week for four type of loads are being forecasted. One is for the city, feeders, factory and houses. And based on the data available to me, I can forecast the tentative consumption in a reasonable area. Based on the smart meter data available to me, I can just understand the consumer's behavior based on the smart meter data and then forecast appropriately. Load forecasting is critical for operations, planning, pricing and hedging in the electricity sector. Higher aggregation level example cities yield smoother load profiles, lower levels example households are more volatile and harder to predict. Very good, because predicting any residential load is certainly a big challenge. Accurate forecast at medium low voltage levels like feeders or smart meters are essential, but they are very complex. Now, if you compare the load forecasting with versus without smart meter data, so if you forecast based on the smart meter data, it's certainly going to be a more accurate one comparing to without meter data. So first of all, when you talk about data resolution, which is, as you could see, that hourly, daily aggregated as feeder system level is squares, where it is fine grain in case of with smart meter data, forecasting targets, feeder level, substation or regional demand, whereas in case of smart meter we can have individual household, buildings and local aggregations. Volatility in handling, it is less accurate and it captures individual uses, variability and randomness. Model suitabilities, it is traditional models are being used, but in case of smart meter data we can use deep learning, sparse models and clustering methods. Now, what is the challenge with the behavioral insights? Limited insight into individual behavior. However, in case of smart meters enables analysis of personal usages patterns and demand response. We are very close to the residents and we really understand how the consumers behave in reality. Weather sensitivity, weather data at aggregate level enables local weather to load correlation model in case of smart meter data. Now, if you use of clustering, it is rare for macro segmentation, but in case of smart meter data, it is essential for grouping similar users, handling time drift behavior. Forecasting accuracy decreases with lower aggregation, however, it increases with high resolution with smart meter data. Real-time forecasting is limited capability, mostly batch mode, but in case of smart meter data, it supports near real-time forecasting and DR responsiveness. Application in DR program mostly aggregated estimation, but in case of with smart meter data, it is targeted prediction for responsive, non-responsive users. So the main challenge without smart meter data is lack of granularity, noisy aggregated behavior, but in case of smart meter data, it is data sparsity, higher noise and model complexity. Evaluation matrix are very standard, which is MAP and MAE, whereas in case of actually specialized MAP, time shift aware error matrix are used in case of smart meter data simulation. Now, moving to load management, because what we are trying to do, for an example, we do experience a peak energy requirement at a substation, and probably we may not be able to cater either during winter peak where there are a lot of heating loads, or maybe summer peak when there are a lot of cooling loads. Okay, so what we need to do, we have to manage the load, because based on the availability of the energy, based on the smart meter data, can my control center, can my server, can my cloud give the direction to the smart meter with minimum analytics to carry out load shifting such that the load curve can be made flattened or load management is possible. So for that, we need to have customer characterization, where smart meter data is used to classify consumer types and infer, demographic informations and predict electricity usage pattern for personalized energy services. And then we need to classify methods like fast Fourier transforms, and then sparse coding and support vector techniques, which are classifying, helps to classify the consumers, such as residents, small as well enterprises, based on their load profiles. Now, estimating load from actually demographics, four users without smart meters, and demographic data, their household size, floor area is used with clustering and regression to estimate typical load behavior. Now, when you move to machine learning and future engineering, feature sets example, average use, time-based ratios are combined with models like random forecast and logistic regression and boosting to map consumption to demographics. Deep learning advances, which is convolutional neural network CNN, effectively captures complex usage patterns and outperform traditional models in predicting the socio-demographic attributes. Now, we can also have a look to illustration of domestic load management based on dynamic electricity pricing in smart houses. So, this is an interesting philosophy I like to explain. Let's say me being a consumer, I do have n number of devices and I do have a smart meter. And the time of use tariff, that means the price of electricity is keep on changing around the day, and the price may be maximum during peak hours and it is minimum during off peak hours. Means when there is a peak, we want consumers not to use further energy, okay, or much more energy. And when it's a price elasticity, means we are price elastic, means whenever there is energy is more costlier, we intend not to use more electricity, and hence I will start consuming less. So when I start consuming less, the peak will come slightly lower. And whenever the energy cost is cheaper, because we are price elastic, so we'll have the intention or intent to use more electricity, so my off peak will be increased. So the instead of running my washing machine during peak hours because it is more expensive, I will prefer to go to a off peak hour to make it is actually more cheaper energy consumption, and that will help my system. So that is what we call actually dynamic electricity pricing in smart homes, where you could see there is a dynamic price server and which through link provides an information where the smart meter understand actually when the energy is costlier or when it is cheaper. So there are multiple sockets, and those sockets actually will behave smartly to act upon. For example, there is an electric vehicle, so the socket will get that information whether to charge electricity for my electric vehicle or not at a given point of time will be decided based on the dynamic pricing. If it is, we do have a period of 24 hours for charging my electric vehicles, then it will choose those 6 hours window where the energy cost is extremely cheaper. So this is known as actually a smart home application, and that is how actually load being managed. But this is possible with help of actually efficient smart meters and getting information for to the circuit to act accordingly. And this is basically a kind of demand response program marketing. So indirect evaluation of DR potential, since application level operation and consumer attributes are not directly observable. So demand response DR potential is inferred using load variability, temperature sensitivity, and consumption dynamics. Now, in case of variability and entropy analysis, models like actually hidden Markov models and entropy matrices help identify consumers with predictable low entropy or flexible high entropy usage patterns suitable for incentive based and price based DR respectively. Now, load reduction estimation, mixture models and probabilistic indices, perhaps actually quantify how much load can be reduced, enabling targeted DR campaign based on expected user behavior and baseline consumption. Now, also it is temperature sensitivity assessment like linear regression and thermal regime models separate temperature sensitivity, example HVAC systems, where the heating and cooling depends on your weather temperature, and base loads to estimate DR potential and identify time period with the highest shiftable demand. So what is the time where actually maximum load can be shifted? And moving to consumer and appliance targeting, techniques like support vector machine SPM and load balancing algorithms identify high consumption users and optimize demand side actions across devices and consumers. So I think what we are really talking about that, when you have an infrastructure, when you have a huge number of data, how those data can be used and acted upon to make sure that the load shifting is possible, demand response is possible, flattening a load curve is possible, and also we need to carry out actually a bit of data analytics to make sure that theft is not there and bad data are being detected. And in case of actually two types of demand response, which is one is popularly price-based demand response focuses on designing tariffs to influence consumers' behavior, as I told you, because if you make the energy cost higher, then I will have that intention not to consume more electricity because we are all price elastic behavior. Okay, so for example, when the energy cost is more, as I told you, or if you see some discounted item online, then we are intent to purchase more products. Okay. Similarly, when the electricity is cheaper, I will switch on all my air conditioners, and when it is costly, then I'll see to that I do not use actually more energy through air conditioning. So that is how actually we manage consumers to behave differently. So while incentive-based DR relies on accurate baseline estimation to measure performance and reward participation. So the cheaper cost means indirectly we are rewarding those consumers. I will just very interestingly put a very interesting example. Like if you go to, Scottish Power, actually they do have a lot of wind energy available to them, and those wind energies are extremely, at its peak during night hours, and those energies are not being used during Scottish region, so they are being dragged into the London side. And at that point of time, actually, they encourage consumers to use electricity more during early morning and late night to consume those excess energy available through wind power at far away point. And to do that, why do I start cooking or, at early morning 4:30 a.m. until unless there is some incentive? So what normally government do, they say there is a huge reduction and sometimes it is free of cost electricity for a particular duration like 4 to 6 a.m. and probably maybe from actually 11 to 1, 11 to 12 midnight. So that is where actually a lot of energy which are surplus available to us can be used. But when you use those energy during those off-peak hours, so probably your consumption of energy during peak hours will certainly reduce because you have finished your, computational work in the midnight and you have finished your cooking in the early morning, and probably the daytime you will not consume an electricity. So that is so-called the incentive mechanism to attract consumers to be more active during off-peak hours. And then we move to tariff design with smart meter data. So once you have all the data available to me, you know how my customers are behaving, and accordingly I can design the pricing. So instead of simply saying the price of electricity is costly at 6 p.m., that will be decided based on the real data. So clustering methods like weighted fuzzy average k-means and Gaussian mixture models are used to derive typical load profiles. Optimization models, including risk-based ones like CVAR, help design profit maximizing and responsive tariffs. And moving to impact of clustering on tariff outcomes, different clustering algorithms and configurations yield varying load grouping, affecting the cost and effectiveness of time of use pricing strategies. So you can now have different tariff structure, maybe, cluster of 4 hours each. I can have actually 6 different pricing mechanism in a day. Currently, the residential customers, for example, we do have maximum 1 or 2 layers of tariff. So probably that can be extended to minimum 4 to 6 layers of tariff based on smart meter data. So there are baseline estimation methods, which are common techniques, include high XOFY, mid XOFY, low XOFY, exponential, moving average, and regression-based baseline studies, so that bias in baseline estimation affect program profitability more than accuracy. And we can also move to advanced baseline modeling, where it approaches includes probabilistic baseline using Gaussian processes, demographic based classification with clustering and decision tree, and optimization based control group sections for fair performance evaluation. So the summary is, it is not very easy to understand the behavior of consumers and their consumption pattern from the smart meter data. So we need to have more advanced algorithms to classify before we create any time of use tariff or implementing demand response activity in a particular distribution system. So with this note, actually we are coming to an end. Thank you very much once again for patient hearing, and looking forward to the next lecture. Thank you. Bye-bye.